Okay, we're going to go ahead and continue our discussion and begin talking about circular orbits. So we're looking at orbits, something like a satellite orbiting the Earth, or something like that, okay? And so we are able to determine the orbital speed by something very similar to our equation in the past. Now, there is a derivation, I believe, in your textbook, but to save time in our lecture, I didn't want to go through all the details. So if you're interested, go ahead and take a look. If not, that's totally fine. I just want you to know how to use these equations, okay? So again, orbital speed is going to be equal to the square root of gm sub e, or the mass of Earth, divided by r, okay, that radius. And remember, the radius is going to include the radius of whatever object is orbiting. So say the Earth, okay? So it's not just going to be the radius from the Earth's surface to the object, but that and the radius of Earth, okay? So then we have orbital period, and remember that period is going to be the amount of time it takes for an object to do one, in this case, orbit. Okay, so that's going to be our orbital period. Okay, so it was found that it equals 2 pi square root r cubed over g m. Okay. All right, so we can go ahead and do an example real quick. 13.9, it states determine the orbital speed and period for the ISS, or International Space Station. Okay, it orbits 4.0 times 10 squared kilometers above Earth's surface. The radius at which it orbits is the radius of Earth plus 4 times 10 squared kilometers. Okay. So what we will do is we'll say the orbit, since we're looking at that first, is going to equal square root of GME over R. Okay. So that will be equal to 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared, excuse me, times the mass of Earth, which we have is 5.95 times 10 to the 24th kilograms, divided by our radius, which is going to be the radius of Earth, just 6.37 times 10 to the 6 meters plus 4.0 times 10. This is going to be 10 to the 3rd meters. So we have 10 to the 5th meters here. Okay, and then that is going to be all inside of a square root. So I'm going to go ahead and do the bottom portion first. So we have 6.37 times 10 to the 6th plus 4 times 10 to the 5th. Okay. Then we have the top, 6.67 times 10 to the negative 11th times 5.95 times 10 to the 24th, and divide that by the bottom piece, and then take the square root of that. Okay, so our orbital speed for the ISS is going to be 7.66 times 10 to the 3rd, and this is in meters per second. Okay, so that is our orbital speed of the ISS. Now we want to know the orbital period. So we're looking for T, and that is 2 pi times the square root of r cubed divided by g m sub e. Okay. So again, we have this guy here. This is going to be 6.77 times 10 to the 6th meters because we did that in the last one. And then G, 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times 5.95 times 10 to the 24th kilograms. Okay. Okay. Oh, and this is cubed actually. Forgot that part. That's important. Okay. So we have that cubed divided by 6.67 times 10 to the negative 11th times 5.95 times 10 to the 24th. Okay, and then we take the square root of that and multiply it by 2 pi. Okay, so we get the orbital period is 5.56 times 10 to the 3rd, and this is going to be in seconds. Okay, now we can put that into minutes. Let's do that. So we've got 60 seconds in 1 minute, just so that we can see this in a scale that we understand. That many seconds just seems like a lot. So let's divide that by 60. And we get the orbital period is 92.6 minutes, which I know is pretty close to accurate. Okay. All right, so let's go ahead and move on now to energy in circular orbits. So by Newton's second law and Newton's universal law of gravitation, we can set those guys equal to each other, sorry, and state also that acceleration is equal to v squared over r. Okay. And then we go ahead and solve this out for mv squared. Okay. And from there, we can find our kinetic energy in circular orbits. Of course, energy is 1/2 mv squared, but now we can put it in terms of our gravitational constant. Okay, so we have gm m sub e over 2r. So our total energy of these circular orbits is going to be kinetic plus potential, and using our potential energy that we found earlier, okay, then we find that our total energy is negative gmme over 2r. Okay. Again, I know that was quick. If you want more details, they have it in the book, okay? Trying to keep this a little bit short and sweet today. So let's look at our next example. We found the change in potential energy. We want to know the total energy of that vehicle from example 13.8, and we can go back to it. Required to take it from Earth's surface and put it into orbit, okay, for a rendezvous. So we basically want to find the kinetic energy and then find the total energy, okay? So let's first find the kinetic energy. Oops, it's okay. That is going to be gm m sub e over 2r. Okay, so 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times the mass, which is 9,000 kilograms. M sub E is 0.95 times 10 to the 24th kilograms over 2 times our radius. Now our radius again is going to be equal to the radius of Earth plus this height here, that 400 kilometers. And we have done this multiple times. We just did it again. And so we get that it's 6.77 times 10 to the 6 meters. Okay, we've done this multiple times. If you don't remember, just backtrack in the notes, okay? So, this is going to be 6.77 times 10 to the 6 meters. All right. So, let me go ahead and put this in into the negative 11th times 9,000 times 5.95 times 10 to the 24th. Divide that by 2 times 6.77 times 10 to the 6th. And we get a kinetic energy of 2.64 times 10 to the 11th joules. So this is our kinetic energy. Okay. So we answered that question. Now we want to know the total energy change. Okay. Oops. So let's go. Oh, no. I guess we didn't do that problem, so I'll have to go back to it. I thought we did. Maybe it was a different one. So we want delta E. So let me go to our textbook and look for example 13.8. Okay, that's right here. That's not the right question. Let me go ahead and find the question that we're on. Let's see. Okay, so it's this question. Okay, so we found the total energy. Oh, I must have used the wrong equation. Let's see. Oh, okay. All right, so our kinetic energy is correct here. The textbook was doing it a little bit differently, but this kinetic energy is correct. And so we just want to find the total energy now, and that is going to be our kinetic energy plus our potential energy that we found earlier. Okay, so it's going to be 2.64 times 10 to the 11th joules plus, let me see it in here. They have that they found it to be 3.32 times 10 to the 10th joules. So 3.32 times 10 to the 10th joules. So let me put that into my calculator. Times 10 to the 11th plus 3.32 times 10 to the 10th. So we get our total energy is 3.58 times 10 to the 12th joules. Whoops. Okay, so this is the total energy required for this vehicle to move from Earth's surface to the ISS. Okay. All right. So moving on, we want to look at Kepler's laws, and there are 3 of them. So let's start with the first law here. Okay. So Kepler's first law states that every planet moves along an ellipse. Okay. And notice that an ellipse is not a perfectly circular orbit, right? So every planet moves along an ellipse with the sun located at a focus of the ellipse. Okay. Now, an ellipse is the set of all points such that the sum of the distance from each point to two foci is a constant. Okay, so let's look at this pictorially. All right, so we have just on a piece of graph paper, we have an X and Y axis, we have 2 foci, okay, and our mass will orbit along these 2 or around these 2 foci, okay. So it's kind of an interesting dynamic here. So it's not just circulating around this focus, and it's not just going around this focus. It's actually going around 2. So we have one mass at F1 and our second orbiting mass here along this ellipse. Now, this is, of course, definitely more extreme than we see, but it is, noticeable enough for us to measure it. Okay, so if we look at the sun over here and our planet, whatever planet is orbiting the sun, okay, we see that we have this same situation. Okay, we have the sun at some focus, F1, and then another focus, F2, and the planet will orbit that entire system here, okay? So it's kind of interesting how our planets orbit the sun, okay? Now, let's look at these 2 terms. We have the perihelion and the aphelion, okay? The perihelion is the point of closest approach of a planet to the sun. Okay, so that would be at this point here, point A. Then the aphelion is going to be the farthest point of that planet to the sun. So that would be way over here. So closer to that other focus. Okay, so let's go ahead and now look at Kepler's second law. It states a planet sweeps out equal areas in equal time. The area divided by time is constant, okay? So what does that mean? So this means that as this planet travels around, it's going to have some v here, right? Some velocity along this guy. Now, as it sweeps along that velocity, it creates some kind of area here, A1. Okay, so if we shade that in, that's going to be A1. Okay, and so it takes a certain amount of time for the planet to travel from A to B. So we're going to call that T1. It takes some amount of time. Okay, now for this second little area, and notice the area looks like it should be smaller. Okay, but it's not. It's the same area here. It's going some velocity, but the amount of time it takes to sweep out that area or go this distance is still going to be your time, T1. Okay. Now, in this third portion, we have an even smaller little triangle looking thing, right? And again, we're going some velocity, but this area is still the same as these other 2. Okay, it's still sweeping out the same amount of area in the same amount of time, T1. Okay, so again, a planet sweeps out equal areas in equal time. Okay. The way that it does this is the velocity of that planet will change. Okay, so it's not just going to be constant v the whole time that it orbits the sun. That velocity is going to change. Okay, so in this first little segment from A to B, it's going to go some velocity v1. Okay, then as it goes from C to D, it has some velocity v2. Now, how do you think it changes? Do you think it got slower or it got faster from A to B to B to C? C to D. Well, it's kind of hard to tell. Okay, so let's go to this third portion. So when the planet is over here sweeping out that area in the same amount of time, do you think the velocity got smaller or larger? Did it increase or decrease? It decreased, right? So we can tell that pictorially pretty easily. We've got this smaller segment here. It doesn't go as far, but in the same amount of time, right? So our velocity is distance over time. And so if this guy decreases, but this stays the same, that means our overall velocity will decrease. Okay, so if this decreases, then this must decrease. Okay. All right, and we can call this velocity, excuse me, the areal velocity. And that is the change in area over the change in time, or length over 2m. Okay. So Kepler's second law is pretty interesting and pretty important here. Okay. Now we look at Kepler. I don't know why I keep saying Newton. Kepler's third law states that the square of the period is proportional to the cube of the semi-major axis of the orbit. Okay, so t squared is equal to 4 pi squared over gm a cubed, where a cubed is that semi-major axis of the orbit. Okay. I don't have any examples on these. They're very straightforward. Just basically in the homeworks, you'll be working with Kepler's third law. But understand Kepler's second and first laws as well. Okay, just understand what they mean, understand their components, what's going on here. Okay. All right. So the last little bit I wanted to leave you guys with is the idea of tidal forces. Okay, so a lot of people, may say this casually, that the tides depend on the moon. And they're not wrong. Okay, they are correct. But sometimes people don't know why or how. And it is all because of gravity. Okay, so if we have our moon orbiting us, right? And we have different tides here. The near side of the moon, so aka when let's just say this face of the earth is facing the moon. Okay, so whatever on the earth is facing the moon, that's how we can say it. Okay, that is going to be high tide. Okay, and then on the other sides of them, so not near side and not far side, but these other sides here, okay, this side and this side, they are going to have low tide. Okay. And then again, on the far side, the moon is going to again have high tide. I'm sorry, the moon is going to cause high tide. So what is going on here? Okay, well, in a basic sense, we've got more gravity, more gravitational forces going on these high tide sections of the Earth. Okay, so we've got the force due to gravity going on here, right? We've got these gravitational forces, and it's making these high tides because the moon is pulling the water more than Earth. Okay, and so this is causing that high tide. Okay, and this is a representation of these forces here. Okay, so we have the moon here. Obviously, this is not to scale. None of this is to scale, but we have these forces that are being pulled, okay, from the moon and the water. So we've got this high tide happening on either end of the Earth, okay? And this is another representation here with the sun and the moon, okay? And so when the moon is in, I would say like, whoops, parallel with the sun. So when the moon is parallel with the sun, at least in like the X, say this is the X axis and this is the Y axis. Okay, so these are in the same axes. We get spring tide. So notice we have spring tide here and here. But then in another case, when they are actually more perpendicular to each other, okay, we have neap tide. And that's basically all I want to talk to you about tidal forces. Very quick, simple. If you want to learn more about it, feel free to look in your textbook. Let me show you something really quick in your textbook that I think will be useful. Okay, so if you're interested, there's also Einstein's theory of gravity, or of gravity, sorry. You can look at that if you want, not necessary, but out of curiosity, go right ahead. I do want to show you in the back here, we have these appendices here, okay? And so you'll be using this astronomical data a little bit. So just notice that you will need to go to Appendix D in your textbook for some data in your homework. And you'll see that there's a bit of data here. We've got the masses of Earth, Moon, and Sun. We have diameter, density, period, distance from the sun. So anything you think you might need, it is there. Notice that this is equatorial diameter and not radius. So just be careful of that. And that's pretty much it for this lecture. Hopefully it wasn't too intense, but I will have this up soon and I will have your next module up. All right, so I will see you on our next Zoom meeting. Have a good week.